All right, so on Monday we discussed more advanced topics in finite difference. And today, starting from today, we are going to be moving to finite volume. So I see in the custom projects, there is actually quite some interest in finite volume, especially for people who are interested in aerodynamics. And so for finite volume, one of the more important things we're going to be talking about is how to extend finite volume, specifically shock resolving finite volume, from only first order accuracy to more than first order. Okay, so to start, let's actually review a little bit of a finite volume, particularly for scalar conservation laws. So finite volume, we start with what's called the conservative equation, the time derivative of the density of a conserved quantity plus the spatial derivative of its flux is equal to 0. Finite volume is specialized for solving this kind of equations. If you can write a differential equation into a form like that, you can solve it with finite volume. Okay, and specifically finite volume discretizes the integral form. So you have to integrate the whole equation, which the time derivative term turns into the spatial integral over a domain. And the spatial derivative gets integrated out. So you get the flux, the difference in flux between A and B is equal to 0. Okay, and finite volume basically discretizes the entire domain into small volumes, right? So this is volume 1 and this is volume 2, etc. So it discretizes the domain into volumes, and instead of storing the values of the solution at the grid point, it stores the averaged values. So Wi would be 1 over delta xi. Delta xi is the size of the volume, right, in the ith domain, and integration from, let's call it xi minus half and xi plus half. So specifically, this is the width of the domain is delta xi, and the location here is xi minus half, xi plus half. Okay, w dx. So this is what we store in finite volume calculations, the averaged value of the solution over a cell or control volume. All right. Okay, so this is all the quantity we know in terms of the computational representation. So the flux, which has to be evaluated at xi plus half and xi minus half, has to be approximated, right? That's the finite volume approximation. So basically, if we set A equal to the left boundary of the cell, B equal to the right boundary of the cell, what we have is d dt of the cell integral, which is actually delta xi times wi, right? Okay, would it be equal, let's just write it as equal to f of w at xi minus half minus fw at xi plus half. And we have to approximate. So let's just write fi minus half, right, which is actually a shorthand for fw at x minus half. We have to approximate it as a certain function. Let's write it as f of wi minus 1, wi, and potentially nearby values of w's, which are all the cell averages. So this is our finite volume approximation. We also call the flux reconstruction. This is all the approximations in finite volume. Okay, so this is kind of a recap of what we have learned previously. Any questions you might have during the several weeks of thinking about finite volume?